Welcome to the lecture series on vitamins and nutrition. Today we are going to look at one of the water soluble vitamins, and we are going to look into different aspects of this water soluble vitamin. And yesterday in the previous session we were looking at this water soluble vitamin pantothenic acid, and today's lecture plan would be we are going to look into the chemistry of this particular water soluble vitamin pantothenic acid. We are going to review back the sources, and we are going to look into the biochemical role of this particular vitamin, and we will proceed further in exploring where this particular vitamin plays an essential role in human physiology, and we are also going to look into the details of deficiency diseases connected with this particular water soluble vitamin. Okay, so with this lesson plan we will start with a little preliminary recap of what we have been doing earlier. So, we saw the fundamental difference between water soluble and fat soluble vitamins. We know that water soluble vitamins are relatively safe and fat soluble vitamins are being stored in liver. So, there are chances for toxicity in case if they are taken in excess. So, we are going to look further into different categories of water soluble vitamins. If you look at this water soluble vitamin, we have already seen thiamine, we have seen riboflavin, and we are looking at the fifth B5 vitamin pantothenic acid. So, we have seen almost these three vitamins thiamine, riboflavin, niacin, and normally we consider thiamine, riboflavin, niacin kind of a pair because their deficiency conditions overlap, and although there is a very distinct contribution by these individual vitamins as a whole, if you look into the overall profile of water soluble vitamins, you find a kind of a close overlap in terms of their availability and also in terms of their biochemical role. And pantothenic acid is supposed to be one of the interesting vitamins because you rarely find any deficiency conditions, and if at all there is any deficiency conditions, you will always pick out a deficiency conditions for the earlier vitamins or the overall B complex vitamins. So, we are going to look at pantothenic acid, and this is the structure of pantothenic acid, and in the previous session I gave a very preliminary introduction on pantothenic acid. It is basically two different chemical components connected together. So, you have the beta alanine structure, and the beta alanine is basically alanine, you know, it is a very good amino acid. It is a simple amino acid, it is a hydrophobic amino acid, and although it is a linear aliphatic amino acid, you have the amino group over here as you see there, and then you have the pantoic acid. Actually speaking, in a common parlance, you can look at butyric acid with the dimethyl substitute over there and the dihydroxy substitute over there. So, it is basically in the linear form on the common name you can call it dimethyl dihydroxy butyric acid. Okay. So, this butyric acid, the carboxyl group forms an amide linkage with the amino group of alanine. So, that is why it is called beta alanine. Okay. So, you have alpha amino acids and beta amino acids. Since it is a beta configuration, we call it beta alanine. So, you have the carboxylic group of the dimethyl dihydroxy butyric acid forming an amide linkage. So, this way you have pantothenic acid, and thereby you have two different entities connected by a amide linkage. Now, if you look into the historical note of pantothenic acid, and certainly Roger Williams should be given the credit of proposing this particular water soluble vitamin, and he did all the preliminary experiments, and although this was not the only vitamin that he proposed quite a series of vitamin and water soluble substituents from yeast. In fact, he was a yeast man, he did lot of studies on yeast, and he tried isolating lot of vitamins, especially water soluble vitamins from yeast, and in that way pantothenic acid was actually a kind of a important hormone which has the vitamin related conditions connected over there. Although it is not a kind of a hormone, normally people misunderstand between the hormone and vitamin. Although hormone is something what we call it as being endogenously synthesized, whereas if you consider vitamin, vitamin is exogenous, it is from a dietary supplement. Yeah, we do synthesize, there is biogenic production, or I would say biosynthesis of many vitamins, but in most cases, let us say we are dependent on dietary sources, or we are dependent on the microbial source present in the large intestine. Now, if you look at this particular vitamin pantothenic acid, you have this particular pantothenic acid, when they tried to purify in the early days, it was little difficult to purify this because the filtrate contained pyridoxine as well pantothenic acid. So, it was at that particular point they knew that they are actually handling with two different compounds, two different vitamins, and that is why it is called filtrate factor. So, in the early days, in the initial experiments, when the systematic solvent based filtration, precipitation and evaporation, and that is how they were doing, compared to the modern methods of HPLC and analytical methods. In the early days, they were relying on the conventional methods. So, you normally end up having sometimes 2 or 3 components together, then they do little more detailed on chromatography separations to isolate these compounds, and end of the day the challenge lies in how you can synthetically make the compound and ascertain the structure. So, that is how we do structural elucidation for most of the compounds, and pantothenic acid was being contributed by Roger Williams. Now, the clinical part if you look at, so you have Conrad, Hivelheim and Jukes. They are the people who were specialists in doing lot of experiments, especially the vitamin experiments in chickens, and we have seen quite a lot of Conrad Evelin's contribution in niacin and other diseases, pellagra and many of the water soluble vitamins. So, that way he actually proved the dermatitis condition. He actually proved the dermatitis condition in chicken, and that was during the World War, Second World War, and that particular point there was a huge demand for vitamin and vitamin fortified food material, because they have to supply a lot of material, and the food material parcel it out to the soldiers, and if they could fortify with vitamins, they could prevent most of the deficiency diseases connected with vitamins. So, here you see the Merck group actually attempted in synthesizing the structure of pantothenic acid. It is relatively simple. Now, the demand for pantothenic acid is normally met in 2 different ways. I would say fundamentally it is met by I would say the synthetic source, and to some extent now they also use the fermentation methods of preparing pantothenic acid, but even now, since the structure is relatively straightforward, synthesizing pantothenic acid by chemical method is still popular. And if you look into the etymology, this also I have dealt in the previous session, and I told you that the very word pantothenic acid basically comes from its occurrence or prevalence in variety of foods. So, that is why you know it is like everywhere, you find them in most of the foods. So, theoretically speaking, getting deficiency for pantothenic acid is quite rare, but nowadays you find lot of advertisements and promotions for pantothenic acid being used in cosmetic industries, and we are going to look at that aspect probably towards the end of our discussion. But I want you to emphasize that certain vitamins, yes, we have to be very clear whether we are getting a dietary supplement, but vitamins like pantothenic acid, it is quite rare to cause any deficiency diseases. But you do have certain conditions which might predispose people, and even if there is a minor deficiency of pantothenic acid which can be completely reversed with dietary supplements, these people show little more or I would say in the higher end of deficiency related conditions or symptoms. Now, if you look at this particular name provitamin B5 or pantothenol is a very popular name being what do you say propagated in the advertisement literature. So, whenever you come across this name provitamin B5, you could very well consider that they are talking about pantothenic acid and pantothenic acid derivative, the pantothenol. Okay, so, here we have this particular vitamin being synthesized and studied well since 1940. And if you look into the food sources, so you see there pretty much you find it in almost every source, okay, from milk, from honey. And very interesting thing to note, in honey, especially the royal jelly as they call it, it is one of the prime food fed by the worker bees. They feed the honey queen bee with this particular material, what you call it as the royal jelly, and nowadays it is becoming very popular as a kind of nutritive food supplement. And royal jelly as a mixture of many water soluble vitamins, and pantothenic acid is one of them. And if you look into the consistency of pantothenic acid, it is quite viscous. Probably the viscosity what you have in the royal jelly can be even attributed to pantothenic acid content, apart from the sugary nature and the fructose and other sweetening components present over there. So, this is one source where you have an abundant amount of pantothenic acid. Now, if you look at other sources, let us say the vegetable sources, the fruit sources and what not, the meat, the egg and all kinds of dietary protein sources, they are all rich in pantothenic acid. Now, if you look into the daily requirements, yeah, you see a periodic increase in the amount of pantothenic acid. We could probably attribute this to development of various internal structures, organs and tissues, and as you have demand for every other vitamin, you also have demand for pantothenic acid as we grow. And a very interesting point to note, we are going to see shortly elaborately on the absorption. So, if you are going to increase the amount of pantothenic acid, let us say tenfold, the absorption of pantothenic acid also decreases to 10%. This is quite what do you say noticeable, and so you do not really end up having any specific advantage of over supplementing ourselves with pantothenic acid, and it is actually not needed except in a case where deficiency diseases are noted. Now, the moment you think of pantothenic acid, so what is the biomolecule that you should connect with? Because every molecule you have a vitamin, you have a corresponding structure to remember with, because they form a very key role in that. The moment you think of pantothenic acid, immediately think of coenzyme A. So, this is coenzyme A, and we will also see about coenzyme A synthesis and how pantothenic acid plays a very vital role in the synthesis of coenzyme. But for you to be aware of this particular structure, so it looks like little big. So, the moment coenzyme A is one of the active precursor compounds, because acyl CoA or the active acetate as we call it is coupled with coenzyme and acetic acid. So, that is acyl CoA, and acyl CoA is one of the fundamental compounds that are essential for all the energy metabolism in mitochondria and what not, in all sorts of reactions connected with the biochemical pathway in energy production. So, you name it carbohydrate, you name it protein, you name it lipid metabolism, this particular compound coenzyme in combination with acetate is the primary material, the starting material even in citric acid cycle. Now, if you look at the structure, if you dissect the structure, you will find the first one, which is basically phosphoadenosine. Okay, so, phosphoadenosine. So, this is the base and it is phosphorylated. So, it is called the phosphoadenosine, and in the third prime end you have a phosphate group attached, and actually this phosphoadenosine is connected by diphosphate link or organophosphate anhydride link with one more compound, and the middle compound, the third one, is basically the pantothenic acid. So, you see over there pantothenic acid on one end, especially the hydroxy end, from the dimethyl dihydroxy butyric acid end, the hydroxy part of it, because the acidic aspect of or the carboxyl group is basically linked with the amino group, we know that, whereas you look at the hydroxy end, they form a link with the organophosphate anhydride of adenosine moiety on the other end. Now, the fourth one is basically the beta alanine. You know that pantoic acid and the beta alanine together, the third and fourth together, they form the pantothenic acid. Okay. So, for pantothenic acid in the middle, you have two different structures on either sides. One, you have the phosphoadenosine, and on the other end you have cysteamine. So, this is basically ethyl cysteamine. Okay. So, you find the free carboxyl group, okay, of the beta alanine forming an amide linkage with the ethylamine, and on the other end you have the thiol group or beta mercapto group. Okay. So, you see there. So, this is the entire structure of coenzyme. Suppose if you want to activate this coenzyme or you want to make acyl CoA, the thiol group would participate in the reaction linking with the acyl moiety. So, this is how a coenzyme gets into a functional mode. So, now you see the essential role of pantothenic acid, because without pantothenic acid you can't imagine having this structure of coenzyme. So, by default now you know the important role of pantothenic acid. So, pantothenic acid is part of the structure of coenzyme A. Now, you know you can actually extrapolate all the functions of pantothenic acid, because all the functions of pantothenic acid are essentially embedded with the functions of coenzyme A. If coenzyme A is not there, most of the metabolic functions will not happen, and if you do not have pantothenic acid, there is no coenzyme A. So, this is how it is all linked. Now, if you look into the absorption of pantothenic acid, so it is present in food either in the free form or as a coenzyme form. The coenzyme form is hydrolyzed to form the free form by intestinal pyrophosphatase. I am going to elaborate more on that, because you need free pantothenic acid, because only the free pantothenic acid can be absorbed in the upper part of gastrointestinal tract, especially the small intestine, and you have this component, what you call it as sodium dependent transport system. You find here in the sodium dependent transport system, the free pantothenic acid goes across and is transported. So, here you find exactly how this happens. So, most of the foods whatever we take, we do not contain pantothenic acid in its free form. Okay. So, they are normally bound along with coenzyme or bound with one more protein, what we call it as acyl carrier protein. So, it is coupled with acyl carrier protein or bound along with coenzyme. So, before you could make this vitamin available for absorption, there are some changes happening in the gastrointestinal tract. So, the vitamin has to be released as free pantothenic acid. So, in the lumen you have this particular change happening. So, the coenzyme and the acyl carrier protein are hydrolyzed to release 4-phosphopantotheniine. Okay. So, this 4-phosphopantotheniine is again dephosphorylated, the phosphate group is removed, and once it is removed it results in the formation of pantethine, and this enzyme, what we call it like pantithinase, then hydrolyzes further the pantethine into free pantothenic acid. So, so much is going on in the intestines before you could have effective absorption of pantothenic acid. Probably that could be the cause. The moment you actually increase the load of pantothenic acid in its conjugated form present in the food. So, if the enzymes are saturated and if they are not able to add more of the substrates to get converted so that you can have free pantothenic acid for absorption, there would be always a delay. So, this is what it is all going on over there. So, first it starts with hydrolyzing and releasing the free pantothenic acid, and it starts in the first step of hydrolyzing to release 4-phosphopantothenium. Then you remove the phosphate group, and then again one more round of hydrolysis to release the pantothenic acid. Now, the free pantothenic acid is available now for intestinal absorption, and you have a sodium dependent active transport system. So, there are different transport systems across the intestinal layers, especially small intestines. So, suppose if you are going to take a more amount of pantothenic acid in the diet. So, the mechanism whatever we have seen now is saturated, and the diffusion occurs via passive mode of transport. Okay. So, if you look into the excretion, so whatever pantothenic acid in circulation basically is excreted in the urine. This occurs after its release from coenzyme. So, since pantothenic acid is basically part of the coenzyme, coenzyme would be processed in the liver, and liver is actually a source for coenzyme synthesis, and taking up pantothenic acid, the coenzyme is synthesized, or I would say constructed in vivo in our body, and when it is eliminated it is reversed again. So, it is released from coenzyme before it could be eliminated. So, if you say the amount of pantothenic acid which have been eliminated, it is like somewhere around 2 mg per day, and you do have, depending on the kind of diet, the amount of pantothenic acid eliminated will also vary. Normally we do not take into consideration exactly how this is done, and in case with deficiency diseases, and when people are being purposely supplemented with pantothenic acid in case to reverse the deficiency conditions, then we go on a very close check of how much pantothenic acid is liberated. Now, if you look at pantothenic acid, this we have already seen how the coenzyme is basically available as a source in the food material, and how systematically it is removed. And if you look into measuring pantothenic acid status, for example, we want to monitor the amount of pantothenic acid available to people. So, what they do is they measure the concentration by on a 24-hour cycle. So, the amount of pantothenic acid is released. So, you take into the time interval how much amount of pantothenic acid is excreted, and in humans the whole blood value is less than 1 micromole per liter are considered as low. So, that is actually a very low level of pantothenic acid, and in case with urinary excretion of less than 4.56 millimole per day is also taken as an indication. So, these are two biochemical parameters that help us. So, the amount of blood pantothenic acid levels and the amount of blood pantothenic acid which was let out by excretion in the renal system, and you take into consideration, and then you calculate the amount of pantothenic acid present in our body. So, generally even if there is any deficiency, the next meal would actually supplement pantothenic acid. This can happen only in cases where there is prolonged fasting devoid of any nutrient intake, and or probably any pathologic underlying conditions where the transportation of pantothenic acid is disrupted, and these incidences are quite rare or probably deliberately envisaged, which is also quite rare. Now, if you look into the structure of coenzyme, which I elaborated, and now coenzyme is basically the functional molecule, and if you closely look at coenzyme, the reactive end, the sulfhydryl end, if you notice it, is that part which is extremely effective in initiating the chemical reaction. So, you now integrate pantothenic acid as part of the coenzyme structure. Now, if you look at coenzyme, where all you find coenzyme, what are all the roles of coenzyme? Okay. So, here you have the enzymes requiring coenzyme as a cofactor, especially pyruvate dehydrogenase complex, alpha keto glutarate dehydrogenase complex, then the FAS complex, thiolase, HMG CoA synthase. Now, we are going to look at that particular aspect. Let us say in the first step in the citric acid cycle, you require coenzyme, and coenzyme interacts with oxaloacetate. The oxaloacetate interacting with coenzyme would give you basically the citric acid needed for the cycle and the very name of the metabolic pathway. So, the first step in the citric acid cycle where oxaloacetate interacting with coenzyme will give you the citric acid. Then the citric acid is like rotated around, in the sense a series of reactions happen and it back generates, you say, the oxaloacetate. Okay. So, this is how the cycle starts. So, here you see how coenzyme plays a very essential role. Now, we are going to look at some more aspects of coenzyme and how this pantothenic acid is synthesized and how pantothenic acid is incorporated into the coenzyme. Before we move on, we would do a very quick recap of what we have done for today's session, and I will give you some questions for you to answer, think about it and answer. So, the first one being, what is pantothenic acid and how pantothenic acid plays an essential role in metabolism. So, the question would be more into on focusing the structure of pantothenic acid. So, what is exactly pantothenic acid, the chemical nature of pantothenic acid? You can write down the question, you can mention the historic background of pantothenic acid. So, how pantothenic acid was isolated as a water soluble vitamin. Then mention all the dietary supplements of pantothenic acid. This is also quite straightforward question. I have elaborated on how pantothenic acid can be assimilated from various dietary sources. Then we also have pantothenic acid playing a major role and the peculiarity of pantothenic acid absorption. So, the question would be, describe on the absorption of pantothenic acid, exactly what kind of functions are associated and how pantothenic acid is made available for absorption. I think in this session we have done with that, and in the coming session we are going to look into the details of pantothenic acid synthesis and the details of how pantothenic acid is incorporated in the coenzyme, and we are also going to look at the aspects of pantothenic acid deficiency. So, thank you for today's session.